Okay, let's get a full screen. I'm going to talk about quadratics. Don't matter. Doesn't matter how many times talk about something. If you keep talking about it, you usually spot things that you might not have noticed before. That continues to happen. I'm going to try to show why the cosine function is the derivative of the sine function geometrically. Why? Because I keep looking at rectangles and squares, and I think I can, but I'm not sure. But that's for a future video. But if you're studying Algebra 1, Algebra 2, or pre-calculus, I think that you should keep looking at the quadratic as much as possible because early calculus concepts come from that geometric shape. And then you can extrapolate to the other calculations we're studying as to how we measure change at an instant. All right, so I'm rambling at the moment. All right, but I guess I'm trying to impress upon you that you have to keep looking at things to deepen your understanding in terms of what you're looking at. You got to just keep looking at things. Okay, repetition is very key. So each of these terms contributes y values to a graph. That's what polynomials are. They're like a tug of war, whether something's increasing or decreasing in terms of table values. There are three terms. When you put it into graphing form, there are two terms. So you have a quadratic term, cup-shaped graph, a linear term. In this case, it's increasing, and a constant, some number. Right? And if you try to figure out how do you add those three up and what it looks like. Well, it's easier to see what something looks like when there's only two things. All right, and if I'm adding the y values, well, when I add this y value, which is 0, to that y value, which is some positive number, well, my graph goes through there. And then eventually I'm starting to add little bits of y values to a constant, little bits of y values to a constant. So it just lifts or lowers a parabola that is then on the x-axis. All right, if I put an h value, h minus h squared times a is 0. 0 is a y value on the x-axis. In other words, it's not positive, it's not negative. So this is always giving us some sort of cup-shaped graph left or right of the origin or at the origin. And then I'm either just moving it up and down. The real action is when we add a linear function to it. Right? And it sure looks like a quadratic isn't changing much right here. But if I add a linear function, right, then those y values, let's say that's the x-axis, then those y values seem to dominate. But eventually, whoo, this dominates more than this, right? There's a y value there, there's a y value up there. So eventually the linear function isn't as dominant a contributor to the numerical change in the table values. But near the vertex, it's controlling the change. And we've done table values to show that. And we'll do some table values over there as well to reinforce that. Okay, so what's happening? Well, I've got two functions both contributing y values that are positive to this constant. Think you're going up faster. You're going to go up faster than the quadratic because this is adding y values to these y values. And we're going to get a narrower quadratic, but on the other side is where the action is. This is contributing a negative value. This is contributing a positive. And the interesting moment is when this is looking backwards now. I mean, this is going down, right? But looking backwards, I'm looking for where here am I going down at the same rate that this is going up? Because when the rates offset each other, I got a flat moment on a curve, right? Pulling something at a negative rate or a positive rate, when they offset each other, marker's not moving. All right, so where's the action? The action is the first two terms, ax squared plus bx. And why is it called a quadratic? Four-sided figure, quad, four in Latin. Okay, there's history behind the evolution of the discipline. And I do fall on the side of evolution. All right. So I can always take out what's common, and what's common here is x So I could write this in factored form as a product. X times ax plus b gets me those two terms. And unfortunately, I can't use square roots for solving equations because that doesn't look like a square to me. Occasionally it could be, right? And I can certainly make it a square with an adjustment plus a constant. That's what completing the square is. It's taking the longer side, making it shorter, adding that, cutting off, it's really evening off the b. It's really the dividing that by 2. Oh yeah, minus b over 2a. Oh, yeah, it does seem like I'm cutting this number in half and then tucking 1/2 here and, oh, I get a square. And we'll do that in a minute over there. All right, but I guess I could always write this as x times ax plus b plus c. That's one term as well. Gives me information too. Gives me a lot of information. Let's look at some of the information that it gives us. Well, let's actually multiply this. Let's just take an x out. X times 2x minus 12. X times, 2x minus 12. That's 2x squared minus 12x. That's good. Now, well, I see some very interesting values here. I see 0 and 6. Yeah, that's no area. So I think I'm going to get C. Well, if I know something about quadratics, then I've got a couple of symmetric places on a curve. Doesn't have to be roots, could be any C. Okay, so let's look at the interplay from a standpoint of linear function, right? X, well, at the origin, they seem to always intersect. I think I could do that with any ax squared plus bx. I think I can pull an x out, which means they have an intersection at the origin. Very good. Yeah. And I can see that this has an intersection at 6. 2x minus 12. That a very important number here, 6. So let's see. I better start drawing this differently. All right. So let's do it right here. So at 0, I'm always going to get an intersection at 0 for this ax squared plus bx. I want to reinforce that. And in this case, I move 6 units to the right. Well, it seems to me that if I have a cup shape, I can immediately see that 3 is the important number to get the minimum, right? The minimum y value. Pretty easy to see. And we're going to practice that at the end of this video a little bit. All right, finding that value. Even a quicker way than minus b over 2a, I think. Fractionally quicker. Minus b over 2a may take, 0.7 seconds. This method might take 0.6. No, we'll find out. But I gave a linear function that's negative here because I want to look at the interplay of the two graphs. Okay, so this is contributing y values, those two y values. This is contributing at the same x, that and that. I think this dominates initially. I think the linear function dominates how things are going to change. In fact, this is always going down at 12:1, whereas the quadratic at 0 isn't changing at all. And I'll show you some table values later to confirm that. So I think the rate of change when I add these two graphs together, actually at the y-intercept, I think things are going down at 12:1. And this is the y-intercept at this instant. Yeah, it's at 0, 0. All right. So what do we do with, guess I talked about that already. So what do we do with this rectangle? We complete the square. And how do we do that? Well, we do 2 times x squared minus 6x, and then you leave a space open and you da-da-da-da-da-da. That takes forever. All right, so we want to look at x times ax plus b, and we want to see what makes zeros. I think we can always say one of the sides of this when it's 0. So I guess the action is ax plus b. And in this case, I could have picked 6. I could have let x equal 6. 2 times 6 minus 12 is 0, times 6 is 0. Or I could have let it equal 0. 0 times 2 times 0 minus 12 is 0. And it's the number in between 0 and 6 that matters. I'm certainly not going to take that approach for completing the square because it takes too long as far as I'm concerned. So how do I put that in graphing form? Yes, we've been using minus b over 2a. Minus b, 12, divided by 2 times 2. That gets us started, right? So that we can write 2 times x minus 3 squared. We can do that quickly and easily. And then what I like to do is I realize that if I put a 0 into this, where's the problem that I'm trying to study? If I put a 0, so I'm way over here. I'm talked about that. So I put some things on the board here, anticipating this conversation. And so I guess this is where we're at. So minus b over 2a, 12 over 4, 3. We get to here. All right. So I can see a 0 gets me 7. I can see a 0 gets me 7. So the completing the square, we've got the square to complete it. Put a 0 in. You get 18 units. You don't want 18 units. You want 7. It's just another way to get the minimum value quickly. And that's how you complete the square. If you did that whole process over there, just cumbersome completing the square. But it's basically getting rid of what you don't want, bringing in what you do. All right, I didn't want 18 units. Get rid of it, bring in the 7, and we've got it in graphing form. All right, that's what you've been practicing. But you also could have worked with the rates of the quadratic, and I'm giving you this problem because I think it will help you understand calculus when you get there. And I haven't done anything that isn't algebra 1 right now. And I'm not doing anything that isn't algebra 1 right here. I'm doing y2 minus y1 over x2 minus x1. And I don't need a calculator for these values. I don't care how many zeros you give me. All right, I've looked at it deeply. There's patterns. And if you look at the patterns, let's just divide by 0.01. That's just the first 3 decimal places. That's going to give us a feeling for slope at that location on a curve. It's just that the change in x is very small. It's just y2 minus y1 over x2 minus x1. And I can see at 0, x squared is changing by 0. It's not changing. At 1, it's going up at 2 to 1. At 2, it's going up at 4 to 1. And at 3, it's going up at 6 to 1. And at 4, it's going up to, oh, did you say 8 to 1? Oh, did you realize that that is how that function is changing at any x value? Sure looks like it. So could I come back here and put all of this together in my mind's eye? Can I look at that and can I say that I know that right here I have a 4-sided figure and I know that one of the ways I can make that area 0 is to use 0. And then the other is taking 1x out. That tells me that 6 is the other root that gets me 7. I shouldn't say root, but 6 gets me 7. I could see that immediately. And what's between 0 and 6? 3. Okay, so I now know that 3 gets me that. Could I plug 3 in? Let's go back to what this was. Can I plug 3 in? Minus 36. But remember, minus 18 plus 7 was what completing the square got us. Okay, so all I got to do is cut that in half and add 7 to get minus 11. And can I look at this now and say, okay, at when x is 0, this isn't changing, but that's going down at 12 to 1. So maybe that's over here going down at 12 to 1 and adding 7. So 0 gets me 7. And looking at how I changed from negative 11 to 7, which is up 18, and the square change is 9, confirming that x value, that a value is 2. There's tons of stuff that's coming from algebra 1 here. All right, so how are you going to understand calculus? You got to understand your algebra 1 and your algebra 2 in order to follow these discussions. And I think you should know that. That what you're doing in the early algebra is going to dictate how well you do later on. I think you need to hear that loud and clear. Okay, and it's a lot more than do this, get that. Math is a lot more than do this, get that. And I think we're diving into it more here. So let's have a little practice over here. with maybe spotting some things more quickly and easily. Okay, I talked about that. So have a go. Have a go. Put that in graphing form, but use rates. All right, are you seeing cup shape up? Now you think about it for a little while, but I'm just going to keep talking. Are you seeing cup shape up? Are you seeing that you're halfway from what makes that zero? And what makes that zero is -2, so that's -1. And if I put a zero into that, I don't usually do it this way. So let me go back. Repetition's my friend. Let's take X. And that is 4X plus 8. Yep, I feel good. 4X plus 8 minus 2. Okay, I just confirming. All right, because I'm going to start doing it this way. I've been doing these for 47 years. I'm changing how I'm doing them. All right, so -1, you put -1, -4 plus 11 should be -7. And I know zero's on this side. And if you put 0 into the rate function is, remember, x squared becomes 2x here. That's how x squared's changing, and that's just 8. So 8x plus 1 is the rate function. All right, and what does that tell me? That tells me that I'm flat right here at what value? Because I want that to equal 0. You tell me what makes that 0. Yeah, it's another way of confirming -1. Yeah, so I'm feeling good about this as a technique. Let me try another problem, see if I can get a little better. Not have that momentary pause. Make it like a flashcard. So let's try it with this one. You have a go at that. See what you get. And I'm just going to talk through it. And I think I'm seeing cup shape up. I think I'm seeing 3x minus 30, which is 10. So I think I'm at 5, halfway there. If I plug 5 in, minus 150, I'm going to do minus 75 plus 11, which is -64. And I think my zero is over here. And 0 should get me 11. And I think I'm going down at 30-1. How do I convert? How do I figure out if that's true or not? I take the rate function, which is 3 times 2x. So it looks like all I have to do is double that. Let's say 6x minus 30. There's my rate function. Let's call it y prime. You're doing a little calculus. When does that equal 0? Confirms that value. And when I plug a 0 in, I'm going down at 30-1, which I guess I can just take from now on there. Okay. Now, you can wait till you get into calculus class and hear that for the first time. I don't think you're going to see the drawings. I don't think you're going to see did I show that? Oh, I've got some table values over there that we looked at. Yeah, I don't think I did this. Or maybe I did at the beginning. But 3 by 3 is 9. And what I'm looking at is adding that layer right there. And what is that layer? Well, let's call that width right there. There's width. Let's call it 0.001. Let's call this width 0.001. That length, I mean, it's a little bit off right there, but it's basically 3 units long. Well, it sure looks like I'm getting 0.003 for this new rectangular area. I'm getting 0.003 for that one. Well, it sure looks like my new area is 0.006. And if I divide by 0.001, yeah, that's going up at 6-1, twice that x value. Yeah, so I can come here and I can say I'm tripling that process. That's why I'm saying 6x. So yeah, if you want to deepen your understanding, then you have deeper conversations. We just had a deeper conversation. It gets deeper than that. Okay, especially when we start changing our x and y axes. What if we had that? And what if that was being squared? Oh, more chats to have down the road. All right, so much for that. And we will upload that. I will upload that and, maybe keep talking about it. And the conversations will get smoother and smoother, just like the pathways in the brain. Toodaloo.